What we have here is a discrete distribution. What the variable x represents is the number of stoplights that you have to hit on your way to work. So for this particular person, there's 5 possible stoplights. And let's say over time, the person's recorded the proportion of times they've stopped at these stoplights. In other words, 0% of the time, 5% of the time, they stop at 0 stoplights, meaning they go all the way through. 25% of the time, they stop at one stoplight out of the 5 possible stoplights, and so on. 5% of the time, they have to stop at all 5 stoplights. Okay, so this assumes that these proportions are exactly correct. So values are now parameters. These are all parameters right now. The 5%, 25, 35, 20, 10, it summarizes this variable. Let's find out what the mean of this distribution is. To do that, since it's discrete, I'll take the value times its probability, and I'll do the same for all of these values, and finally I will sum them up. Now this value is the mean of this distribution, but to be more precise, it is the population mean. Notice I'm using mu and mu sub x. The variable here is x. This is the mean of that variable. Likewise, I can find the standard deviation by doing the following. I'll take the probability times the value minus the mean, square it, and now the standard deviation will be the square root of this sum. And again, to be clear, this is the population standard deviation. Okay, now let's say that I sample from this scenario. In other words, I actually go to work and I start figuring out for that particular day how many stoplights did I hit in that day. So we're going to simulate that. So I'm going to go to Data, Data Analysis, select Random Number Generation, Number of Variables. I'm going to do this once for the moment. Number random numbers, 35. The distribution is discrete. The parameters are these values, the actual value and its probability. These are my parameters. The random seed, let's say I choose again some number to get this thing going. And my output range, I'm going to just put it right here at A21. So hit OK. And this becomes one sample of 25. One thing I could ask is, well, on average, how many stoplights did I stop at on my way to work for those 35 times I sampled? In this case, it was 2.05. So this value here is x bar. It is the sample average. This value is really an estimate of this value right here. The bigger the sample, the better the estimate, because my variability will again go down. But one thing we want to understand is, what does the sampling distribution of x bar look like? In other words, to describe a distribution, you got to find out what its shape is. Another way to describe it is finding its mean. Another way to describe it is finding the variability, standard deviation. You can also figure out how many outliers or where the outliers are at, but we're not going to go that far. We just concentrate on the distribution type, the mean, and the standard deviation of the distribution of averages of size 35. To do that, we have a theory, but we're trying to illustrate that theory. At least we can tell you what the theory is. We're not going to prove it mathematically. We're just going to show you instead. The proof is beyond the level of this class, but it's easy enough to convince you that this is possible. So I'm going to choose random number generation again. Again. Everything's going to stay the same just about, except I'm going to increase. Let's say I'm going to do this 274 times more through this process of sampling 35 at a time. My random seed, I'm going to change to something else for the moment. And my output range, I'm going to just put it right next door and hit OK. So I'm going to create 275 iterations of sampling 35. So I hit OK, and here we are. So now I'm going to find the rest of these sample averages. And here they are. Now, let's talk about the distribution. Let's talk about the distribution of the parent population. The distribution of the population, you can see it is slightly right skew. And to see this a little better, let me create a picture of it. Again, this is perfect. This is supposed to be the exact population. And you can see it, oops, if you can see this right here. Again, the variable x is at the bottom. Okay, this is number of stoplights. That's what my variable x is. And you can see this distribution is right skewed. Okay, now let's suppose I create a histogram, but of these values you see right here. These values come from this parent population. So in reality, it should look exactly like this, or not exactly, but that's the shape it should take because I haven't done anything. This is my raw data right here. It comes from this parent population, so therefore it will take the shape of my parent population. And again, to show you this, I'll just come over here anywhere. It doesn't matter where. I'll just grab a swath anywhere, doesn't matter, and create a histogram of it. So I'm going to go again, data analysis. I'm going to choose histogram. Input range, again, I'm just going to grab a set of data since it has to be in one block. I'll just grab a block here. Okay, that's good. That's good. Oh, where am I? There it is. There's the block. Actually, I just let go of the block. Alright, so now I have a nice big block I've chosen. Bin range, I'm going to let the computer figure this out. Output range, I'm going to put it below here so it's out of the way. I want to click on chart output. Yes, I want a chart to come out of this. Hit OK. And where's my chart? Okay, it's probably up here somewhere. Okay. There it is. Oh, actually it's next door to this one. Perfect. So here is a histogram. Oh, here is a histogram of this distribution, and you can see it is taking on that shape. If I did another histogram just for fun, another swatch somewhere else, I'll still get, not exactly the same picture, but around the same picture. So I go back to data analysis, histogram. Let me go back and pick another spot here. So I'll just start right here from the middle. Output range, just put it below here and hit OK. See where that, oh, did I not click chart? Where'd it go? That's always fun figuring out where these charts go. Oh, there it is. Gosh. There it is again. You can see it's the same picture. Relatively speaking, it's the same shape. It's not exactly the same shape. But again, we were expected because this is a sample. Okay. Okay, so that's what the parent population looks like. Let me delete these. But that's not what we're after here. when we average them, we're in essence creating a new distribution. What does this new distribution look like? Well, let's create a histogram of these values. And I'm going to actually move them somewhere else for the moment. I'm going to move them below here. I'm going to just transpose these so they're just numbers. Okay, so here I have my averages. One thing you notice that a lot of them are just twos or very close to 2. In other words, for examples of 35, I'm getting closer to this value 2.2. So most of my numbers will be close to 2.2. The range, possible range, you can see here the possible range of single values, but the range of averages of 35 will be much smaller. So let's create a quick histogram of this. Data analysis, histogram. I'm going to select my averages. I'm done with that. See, I'm just kind of glancing a quick look here. I should have created my own bin range. I'll do that real quick. I'm guessing here as to the smallest and highest values. Make it, I just make it nice even numbers. Okay, that's good. Okay, my input range are these values here, my averages. Hopefully I did a good job with the bin range. Output range, let's just put this right here. Hit OK. And here's my graph. Well, I'll put it next door to this one. You'll notice now it's taking a little different shape. Notice it's more symmetrical. It certainly looks way more symmetrical than this original parent population. Is this close to normal? Well, the picture seems to indicate that, but we could be fooled with this histogram picture. So I'm going to create another picture where I cannot be as easily fooled. So I'm going to grab these numbers and create a normal quantile plot. I'm going to just paste these here. I'm going to enumerate these values. Don't worry if we've never gone over this, so do not worry about it. Oh, I should have done this instead. 1, 2, 3, not start at 0. Now to find the expected z-score, I'm going to use this particular formula. That gives me a z-score, norm as inv, but the formula says take the position minus 3/8 and close it, divided by 275, my sample size, 0.25. And I'm sorry I said the word sample size. There's a lot of things going on here. Oops. Yeah. For our conversation, the sample size is 35. These are my expected z-scores. These are my values. I also need to order my data values. Since the z-scores are ordered, these need to be ordered as well. And now I'll create a scatter plot of these two, expected and the actual sample average is 35. I'll create a scatter plot of this, and here we go. You can see this is nice and straight. All indication says that yes, this distribution of averages of 35 is very, very close to normal. Now, it cannot be normal because the distribution of averages of 35, since the parent population is discrete, so is this. So this population is discrete, normal populations are continuous. But the shape certainly looks normal. And the central limit theorem says it cannot be normal, but it can be approximately normal. And you can see from this picture that it's very close to the shape of a normal distribution. Okay. All right. So now we can do the last piece. So the shape of the averages of 35 has a normal looking shape. The next question is, what is the standard deviation? What is the mean? Okay. I want to know what the mean of the averages is. I want to know what the standard deviation of the averages is. Theory says if the method of sampling is unbiased, then the mean of this distribution should be equal to 2.2, the mean of the parent population. So I cannot prove to you that's the case here. The best I can do is, because I have such a large sample, I can just take the averages of these averages and just show you that it comes very close to that value. So again, this is not a proof. This is more of saying that yes, this seems plausible. What I'm saying to you is plausible. So indeed, this is just an average, another statistic basically, a statistic of a statistic. And as you see that it comes to 2.189. Again, there's only 275 numbers here. What about the standard deviation? Well, theory says it should be the old standard deviation, this one, divided by the square root of my sample size, which is 35. Notice it is the sample size of what generated the averages. It is not the number of averages I've generated. Big difference here. So I enclose it, and that's what theory says I should have. Again, I don't have the ability to come up with this number because it's a perfect number. It is a true value. If I could sample forever, an infinite set, I can probably do it. Come very close, but I can't do an infinite set. So instead, I'll just take another statistic here. I'll take a standard deviation of all these averages, and it should be very close. So all I'm trying to do is provide some impetus or some plausibility to what I'm saying. And there's my sample standard deviation. So the thing you got to get in your head is there's a lot of things going on here. When I sample, when I do this in real life, this is my sample of 35. But every sample you got to think of coming from a particular population of more samples of the same size. The question becomes, how do all these potential samples vary? I believe it's chapter 18 in your book where the author makes, I think, the best descriptor possible for this situation. In that very first paragraph of that chapter, somewhere there, he uses the word imagine. So when we sample, we realize that even though we have only one value, like this mean, for example, this sample belongs to a larger group of all potential samples you could have taken, even though you'll never take them. And so you have to imagine that this comes from a much bigger set. So the purpose of this is to show you the concept of the central limit theorem applied to centers.